So that's the thing that we will discuss today. Okay, wedge. Okay, I will repeat again. The purpose of a wedge is to keep one thing, like this particular pipe, right? A metal pipe in one position. And how does it works? Actually, it incorporate the friction there in order to keep the things that we want to keep at one particular place stay there, to be able to stay there, right there. And beside this one, sometimes wedge is used in order to keep the door at particular place as well. Normally we will put it here, like at this particular position, those wedge. And the shape is normally like this. Okay. Any question about this?
Sir, when will the third exam be held?
Third exam, I believe, is supposed to follow what is given there in your schedule, 20th of May.
Okay.
Oh, 20th of May. I already explained it at the beginning of the class.
I forget. Thank you, sir. Sorry.
Okay. Any question? Any other question about this? About wedge? Okay. About the what is wedge actually? Okay. So please later when we discuss about it, don't think about what your friend use, okay, as their shoes like that. Okay. So it's something else. Okay. What's here is something we use to keep something else at one particular place instead of the type of shoes like that. Okay. So this is one particular example, the easiest example of wedge. You can see, right? There is a mass here. Okay, there is a mass there. And we want to use the wedge. Okay, we want to use the wedge to raise the mass. Okay, to raise the mass. Okay, we want to raise the mass from at the beginning it's touching the ground, and we want to raise the position of the mass. Okay, so instead of using anything else, we use wedge. Okay, we use wedge, and what will be happening there? Okay, of course we have to take a look at the free body diagram of the wedge itself and the mass as well, if it's necessary. Sometimes looking the free body diagram of the wedge will be enough, but sometimes we have to take a look at the free body diagram of the mass as well. Okay, so if I ask you guys, okay, what is the force necessary here, the force P, the value of the force P necessary to move the wedge in order to raise the mass? How can you answer that? Nuki, seems like you are a bit confident about your second exam, right? So I believe you must have a confidence on answering this as well, right, Nuki?
I'm not confident, sir, but I'm still, well, consuming the information right now, sir.
Okay, try to think about it. What is the first thing that we're supposed to do in order to answer my question just now? Because as I told you, yeah, a wedge is actually used to keep one particular things at one particular place, or the same as this one as well, to raise the location of that things as well. So here we want to use the wedge to raise the position of this one, this mass.
We're going to raise the block going up, right, sir?
Yes.
And that pin going to help it roll going up, I presume.
Yes, yes. But the question is, what is the value of the force necessary to raise the mass. So basically, as long as the wedge can go in, it will raise the mass, right?
Yes, sir.
Okay. So what is the condition for us? What is the condition of the wedge to be able to go in this kind of position?
You need to have force that bigger than the friction happen between the block and the wedge.
Yes, correct. Not just the block and the wedge.
And the floor.
The friction, yes, correct.
And the floor.
Because the friction is happening at this particular surface, right?
Yes.
This is the principle of the wedge, right? The friction happens on that particular contact between the mass and the wedge. And the second one, the friction is happening as well here. Okay, the friction happening as well there. So it's between the wedge. It's between the wedge and the ground, right? It's between the wedge and the ground. So we have two friction surfaces there. So between the mass and the ground, between the mass and the wedge, and between the wedge and the ground. So that's the thing that we have to concentrate about. Okay. Yes, then after you know the principle, can you draw the free body diagram? Okay.
Yes, sir. So okay. Since the force coming from the right, so the friction between the wedge and the floor should be going to right.
Okay,
while with the block going to the left.
Okay, so this is the wedge, right? That we are talking about. Then we have P here. Okay, what else that we have there?
Friction between the floor and the wedge going right.
Friction between the wall or the wall. The wall?
Between the floor and the wedge.
Oh, the floor. Okay, between the floor and the wedge, there is a friction. But in order for us to have a friction there must be something else, right?
Yes.
Because friction force is supposed to be...
It needs normal force.
Yes, correct.
It needs normal force.
There is a normal force there. There is normal force 1, for example. Then, because of there is a normal force here, there is a friction force here.
Friction force there. Then the normal force 2.
Okay, friction
between
force
the wedge and the block, sir.
Okay.
Are we still
where's the direction for that one?
Going down.
Going down, right? But not actually going down, right?
Yeah.
Because it's supposed to be perpendicular to the surface, right?
Perpendicular to the surface of the block.
In an angle, yes, sir.
Yeah,
correct.
It's angular.
This one, for example,
with alpha as its angle.
Alpha, yes, correct. This one is normal.
2.
Normal force 2.
And the friction.
This one is alpha.
Going to the right too.
Oh, and then the friction as well here. Friction 2. So basically, this is the free body diagram, right?
Yes, sir.
Okay. So, and you have to remember that there is an alpha here. So if I ask you what is the force P, the value of the force P to be able to raise the wedge, what is the answer there?
We use sigma Fy equal to 0, sir.
Fy?
Fx, I mean Fx equal to 0.
Fx, okay. But wait a minute. Have we know the value of this?
Not yet, sir.
This.
Not yet, sir.
Okay. So the first thing that we supposed to do, right, is to find out the value of the normal force. Yeah. So for the normal force 1, what is the value there? If the wedge is have no mass, we assume that the wedge is
So
have no mass, then there is no mass of the
no
wedge.
normal then.
Huh?
If there's no mass, so the normal force is
No, we cannot calculate this
normal
force here.
force one. There is no normal force one.
No, there will be, but the calculation is not like that.
But,
okay.
Oh, we are using the normal force 2 to get normal force 1.
Yes,
so
but in order to do that, we have to find out for normal force
2 and normal force 2 we get from the mass of the block.
Yes. So
And
we
the
have to
mass-
draw. We have to draw the other free
the
body diagram.
free body diagram of the block.
Yes, correct. This one, in order to find out for the normal force 2. So normal force 2 is supposed to be like this, right?
Yes, sir.
And the friction force is supposed to be going the other way, right?
Yep. And weight.
There will be weight, yes.
Weight.
M multiplied by G, right?
G, yes, sir. Then the roller on the wall.
And the roller, yes. Then the roller of the wall. Then for this one, because there is no friction there, I will put just one force in order to represent the roller force on the left and the right. Okay.
Okay.
So this is roller reaction. R.
So
okay.
we got
how many unknowns? How many unknowns
we got
have here?
4 unknowns.
No, we don't have 4
I'm
unknowns.
sorry.
M here is known.
M is known, so we got the resultant we don't know, and the normal we don't, and the friction force. So we got 3.
Actually, yes, correct. The friction force, resultant, normal force. But actually, we don't have 3. Actually, we have only 2, because friction force here, in order
after
for,
we get normal.
In order for the P, in order for the wedge can be going inside, right? The friction force here is supposed to be the same as the maximum friction force, right?
Yes, sir.
Because it's supposed to handle the bending motion condition. So the friction force there, F2, is supposed to be, right, equal to N2 multiplied by mu S. So basically, the number of unknowns that we have here is only 2, R and N2, right? And can we solve it using this sigma fx equal to 0 and sigma fy equal to 0?
Yes, sir, we can.
Yes, we can.
But we need to project the N2 first, since it's have angle.
Yes, of course. Okay. After you solve for N, who's this?
Azhar.
Okay, Asaf, yes.
Why you use mu S instead of mu K?
Because the condition at the beginning is it's stationary and it's supposed to be starting to move. So what is the minimum force given there as a P? Okay, in order to ensure that the wedge can go in. Okay, if at the beginning is stationary, then we have to make sure that the wedge, the force can handle the maximum friction force. Correct or not, Azhar?
Yes.
That's the logic behind it.
So why you use mu S is because it started on a stationary position.
Yes, of course. Everything started at a stationary position, right? And beside that, because it's started at the stationary position, that's one thing. The other thing is the maximum friction force. The maximum friction force happens when the coefficient of friction is actually same as mu S, right?
Yes, because mu S is larger than mu K. Yeah?
Yes, correct. So remember when we discuss about the value of the friction force against the given force like that. So it's like this, right? It's going constant like that. Then after that it drops, yeah, and then it drops. Then like this, right? Okay, this is the value, the maximum friction force value. The maximum friction force value is supposed to be normal force multiplied by mu s, right? This one.
Yes.
So as long as the given force can handle, okay, the maximum friction force, which is normal force multiplied by, normal force multiplied by mu s, okay, then it will be able to move. We can ensure that it will be able to move, right? Correct or not, Asar? So that's the principle that we will going to use for dry friction and wedge. Okay, when the question is, what is the force needed to move the things? Okay, the first thing that you have to check is this one, the maximum friction force, whether it can handle the maximum friction force or not. Because as long as it can handle the maximum friction force, yes, it will be able to move. You understand, Asar?
Understand, sir.
So that's the thing, right? By using sigma fx equal to 0 and sigma fy equal to 0, for sure we will be able to solve for N2 and R. Correct, right, Nuki?
Yes, sir.
Yeah, correct, right?
Yes.
Using sigma fx and sigma fy equal to 0, then we will be able to find out the value of R and N2, right?
N2. Then after that, we get back to the first free body diagram.
Yes.
And we find N1 and F1. Then we can find P by using sigma fx equal to 0.
Yes, correct. So basically, this is after you find N2 and F2, right? After you find N2 and F2, this one is already known, right? These two values are already known. And
Yes.
remember, F1 here is the friction force, the maximum friction force as well, because it's from a stationary position. So the friction force there is supposed to be the maximum friction force, right? So the F1 here is supposed to be the same as N1 multiplied by mu s as well. Okay, okay?
Yes, sir.
If N2 and F2 is already known, how many unknowns we have here in the first free body diagram?
Only
After
one.
we
Sir.
solve the second. Huh?
Only one.
No, not only one. We have two. P
I mean,
and N, right?
2 and N1. P and 1. Yes, sir.
Okay, the same as before, we can solve it using this. Sigma fx equal to 0 and sigma fy equal to 0, right?
Yes, sir.
Yeah, after we solve it, then yeah, we know the value of P.
So if I calculate some, so the F1 should be mg cos alpha over sin alpha time mu s. Meanwhile, the F2 should be mg over sin alpha time mu s, sir.
Most likely, I'm not sure about that. We have to calculate again. Later in the problem example, we will know about it. Okay, but
yes, sir.
This is the principle of it, right? Do you get it?
Yes,
okay?
sir.
So basically, if we want to put the wedge in, we have to draw the free body diagram, okay, which consists of the normal force, friction force, and the friction force there is supposed to be the maximum friction force, which is the same as normal force multiplied by the mu s. Okay?
Okay, sir.
So basically, these two, friction force and normal force, is actually just representing one unknowns only. Because as long as we know one and one, F1 will be known, right? So this one is actually just one unknowns. And this one is just actually one unknowns as well. By knowing N2, F2 will be known. Correct, right? Okay?
Yes, sir.
Yeah. So later we will discuss, we will continue our discussion based on that. Okay? Anyone else here want to ask question about the discussion on the wedge here? Okay, this is the basic theory of the wedge. So if you want to put the wedge in, okay, this is the free body diagram that will be happening there. Okay, this is the first free body diagram. Okay, Unfortunately, from the first free body diagram, we will not be able to solve the problem because there is N2 and F2 there. That's why we have to draw the second free body diagram, which consists of the mass and the friction there. Using the second free body diagram, we will be able to solve for the resultant force at the roller and the friction force as well as the normal force too. After solving the friction force and normal force too, then we can go to the first free body diagram again to solve for the normal force 1, friction force 1, and the force P, which we need. So we will be able to solve force P here. So basically, that's the principle behind it. Okay. Any question about this?
Sir, so the normal force on the wall is canceling each other, right? Yeah.
Normal force on the wall. In this case, there is no normal force on the wall because, normal force on the wall.
Yes, from the wall. Is it? There is any? Is
Yes,
there
yes,
any?
R here. R here is actually
Yes.
the normal force on the wall.
But from the
But
right,
there is no
is
friction
it?
force. From the right, it's because of there is a normal force on the left and normal force on the right. What I draw here is just the resultant of both. R there is actually the resultants of R1 and R2 here. Okay?
Oh, I see.
Because they are happening at the same line of action, okay? R1 and R2 happening at the same line of action. That's why I can represent it using just one force.
So the R on the left and the right will be the same, right?
Nope. It will not be the same. Because if it's the same, then the value of R will be 0.
Oh, I see. Okay.
It can be. It depends on the condition, right? Sometimes the left R will be bigger than the right R, but sometimes the right R will be bigger than the left R. Okay. Depends on the whether you are putting the wedge in or pulling the wedge out.
Oh, I see. Okay.
Okay, you get it.
Okay, sir, I get it.
Any other question here about the theory of the wedge in order to put the wedge in? Shabina, do you have any question?
I'm still processing, but for now, there's no question, sir.
Okay. How about you, Raihana?
No question either.
Okay. Then in that case, I will continue. So, like I said before, right? Because the friction force, okay, because the friction force which is happening on the surface, okay, because the friction force which is happening on the surface depends only on the normal force. Why it's depend only on the normal force? Because the one in question for the wedge is always what is the force to put the wedge in and what is the force to put to pull the wedge out. So most of the time we always deal with condition of impending motion. We always deal with the condition of impending motion for the wedge. Okay, for the wedge. That's why most of the time, okay, the friction force is always, most of the time, the friction force is like this. Normal force multiplied by mu s, directly like that. And because of that, because of this, right, because mu s is already known from the beginning, friction force will only depend on the normal force. Okay, in that case, we can represent both normal force and friction force just using one unknowns, right? Because friction force is just normal force multiplied by mu s, and normal force is just normal force. So basically, if you take a look at the R1 here, please take a look at this. This one is actually the representation of the first free body diagram that we draw before. Okay, this is the second way to represent it. The first way to represent the free body diagram, the first free body diagram is like this. Okay, like that. There will be a normal force, friction force 1, normal force, and friction force 2. But friction force 1 is actually normal force 1 multiplied by mu s. Friction force 2 is actually normal force 2 multiplied by mu s. Okay, that's the first representation of the free body diagram. The first way to do the free body diagram. But there is another way. Okay, the other way is like this. This is still the same, the first free body diagram, but in order to represent the friction force and normal force, we can just put it as one force. So basically, R1 here. I think I will just put it with using another color. Actually, R1 there is just the summation of normal force 1 and the friction force 1. Okay, normal force 1 and friction force 1, if you sum both together, what we will get is R1. Then normal force 2, this one, and then friction force 2. If you sum both together, what you will get will be the R2. So actually, we can represent normal force 1 and friction force 1 as one unknowns. In this case, is R1. Normal force 2 and friction force 2, we can represent it as one unknowns. In this case, it's R2. Like that. Okay. The same if we take a look at the other free body diagram. The second free body diagram here is actually this is the friction force 2, and this is the normal force 2. Okay, and if you sum both together, what you will get is the R2 like that. So basically, although this one is the second free body diagram, this one is the first free body diagram. Although in the second free body diagram, previously, we have N2, F2, R3, right? Seems like we have 3 unknowns there. But actually, we only have 2 unknowns, R3 and R2. This one is R before, right? We have only R and R2. Okay, we have only R and R2, where R2 is actually representing the N2 and F2. Okay, so basically we only have 2 unknowns from the second free body diagram. Then we can solve it using sigma fx equal to 0 and sigma fy equal to 0. Remember, we don't have sigma moment here. In this case, we don't have sigma moment because all of our calculation is just based on the point calculation. So everything is assumed to happen at one particular point. So we only have 2 equations, sigma fx and sigma fy equals 0. Then by solving R and R2, okay, then we can use R2 in the first free body diagram to solve for R1 and P. using sigma fx and sigma fy equal to 0. Okay, this one is sigma fx2, 1, fx2, and this one we have sigma fx1 equal to 0, sigma fy1 equal to 0. That's it. Any question, boys?
Will the angle phi, angle phi be determined when, I mean, the angle will change if the normal force is changed also, right?
Okay, so phi there, right? Phi there. Can you guess what is phi actually there?
The resultant of normal and the friction, right?
And what is the
And
angle
then
there?
I guess you could use tan inverse, sir.
Okay, let's try to draw it. Okay, let's try to draw R1. Okay, the assumption here is all the mu s is the same, right? The assumption here, all the mu s is the same. Okay, let's try to make the this particular drawing bigger. There, okay. We have N1, F1, and R1. Okay, so this is N1, and this is F1. And F1 here, the value is supposed to be the same as N1 multiplied by mu s, right? Correct, right? And then if you sum both together, what you will get is R1.
Oh, sir, so the angle will only be affected by the factor of mu s, yeah?
Yes, correct.
Oh, okay.
Okay, and now let's talk about the angle. The angle is this angle, right? This is phi. Can you tell me what is tangent phi there, Matthew?
The friction over the normal force.
Friction. F1 divided by N1, right? It will be the same as what in this case? N1 multiplied by mu s divided by N1. Correct, right?
Yes, sir.
So tangent phi in this case will be the same as mu s. And it will be applied for all the calculation. So the tangent phi there will depend on the friction force on that particular contact. So the tangent phi here, the tangent phi there will be the same as mu s of that particular contact, okay? The tangent phi here will be the same as the mu s at that particular contact as well. You get it, Matthew?
Yes, sir. Yeah.
Sir,
So that's
I
the thing.
understand the triangle in the C part. What
See.
is
No. You don't have to take a look at this.
Oh, okay.
No. This one, please don't take a look at this. This one is not important. Actually, yes, you can understand something for that, but it will confuse you even more. So just try to concentrate on this only, okay? So there are several ways for us to handle this particular problem. The first way is to separate the normal force and the friction force, okay? But remember that the friction force is actually normal force multiplied by mu s, because we always consider the condition of impending motion in this case, because it's always moving from stationary. So if you are more comfortable of using this particular free body diagram, the first free body diagram, the first way of drawing the free body diagram like this, normal force is there, friction force is there, but the friction force is normal force multiplied by mu s, okay, directly there, then you can use it. But what you have to remember is one thing. These two, we can consider it as one unknowns. These two, we can consider as one unknowns as well. Why? Because the friction force depends only on the normal force. Because the friction force there is the normal force multiplied by mu s. The same as this one as well. These two forces is actually just one unknowns. Because the friction force depends only on the normal force. The mu s, because it's just like normal force multiplied by mu s, and the mu s is actually known value. So both ways are correct. Drawing the free body diagram like this, like in this particular page, is correct, or drawing the free body diagram like in this page as well is actually correct as well. It depends on which way that you are more comfortable with. Okay, do you get it, guys? Any question here? Hello?
No, sir.
No. Okay.
Pak,
Yes.
do you use mu s because the question is not stating that the wedge is already moving?
We always use mu s because our assumption is at the beginning is always in the stationary position.
Because last CL, the question states that the object is already moving.
Yes, sir.
In that
That is
case,
what I'm asking too before.
okay. If there is nothing there, means that you have to assume that the object is from stationary. Okay, if there is nothing, no statement there, which means the problem is just like as it is, there is no statement about the moving everything, then you have to assume that everything is everything started from stationary position. But if it is stated there that the condition is OED moving, then in that case you have to use mu k then. Okay.
Okay, sir.
But
so
most of the time, normally we use mu s because most of the time is a stationary position. Okay.
Okay, sir. So theoretically, if we already exceeded the impending motion state, we can reduce the force P and the object will keep on moving, yeah? Yes.
But if P value is still the same as the impending motion force, the force needed for the impending motion, then it will keep moving, right? Because the friction force is less than the impending motion friction force, right? So we can ensure that it's moving in, right?
Yes, sir.
But normally the limit is at the impending motion because the limit is normally happening at when the friction force is at the maximum state. Okay. Any other question about this? Before I discuss about the condition that you need to know. No? No more question? Okay. In that case, I will just continue then. Okay. So this is actually the free body diagram. Okay, the free body diagram of the mass and the wedges. The free body diagram of the mass and the wedge. When we try to raise the mass, when we try to put the wedge in, right? Okay, but there is another condition. Okay, there is another condition. What if we want to pull? We want to pull the wedge out. We want to pull the wedge out. What we supposed to do if we want to pull the wedge out? How can we draw the free body diagram? Okay, how can we draw the free body diagram? Okay, so this is it. This is the free body diagram when we want to pull the wedge out. When we want to pull the wedge out. So basically, there will be same R1 and R2, but the direction will be different. Why the direction will be different? Because if we draw the normal force and friction force separately, okay, if we draw the normal force and friction force separately, this is what we will get. Okay, the P is pulling the wedge out, then there will be normal force 1, then there will be a friction force 1, and the friction force 1 is supposed to be going to the left instead of to the right, right? Because the pulling force is going to the right. Then beside that, okay, beside that, we have a normal force as well. Normal force to like this. And then the friction force is going to the left as well. Okay, this is the free body diagram of the wedge. If you want to separate the drawing of the friction force 1 and the friction force, the drawing of the the normal force and friction force. But remember, as usual, these two is actually just one unknowns, and these two is actually just one unknowns, because we're supposed to represent F1 here as normal force 1 multiplied by mu s, F2 here as normal force 2 multiplied by mu s. Okay, the same as well if we are talking about the mass. Okay, if we are talking about the mass there, if we are talking about the mass, then we have to draw the mass as well, because we will only be able to solve the problem by solving the free body diagram of the mass first. Okay, then in this case, what we will have is mg here. Then there will be a resultant of reaction force R here, R3 here. Then there will be a friction force and normal force. Okay, normal force like this, and then friction force like this. Where friction force 2 is actually equal to N2 multiplied by mu s. Okay, so this is what is happening if we want to pull the wedge out. So this is the free body diagram if you want to represent friction force and normal force together. And this is the free body diagram if you want to represent normal force and friction force separately. But remember, the normal force and friction force there is one unity. I mean, it's just one unknowns. We can consider both as one unknown. So normal force and friction force 1 we consider as one unknowns, where the friction force 1 is equal to normal force 1 multiplied by mu s. Normal force 2 and friction force 2 we consider as one unknowns, where the friction force 2 is actually the same as normal force 2 multiplied by mu s. That's the thing. Okay, this is the two conditions that we normally have to deal with. Because when we talk about a wedge, we need to put the wedge in and we have to pull the wedge out. Sometimes those are the conditions that we normally do. Okay, push the wedge in and pull the wedge out. Okay, about pulling the wedge out, anyone want to ask question? The way to solve it is the same as before. In this particular free body diagram, we have two unknowns, R3 and R2. Okay, we can solve for R3 and R2 using sigma fx and sigma fy. Then, in this particular free body diagram, after solving R3 and R2, we only have two unknowns there, P and R1. So we can solve for P and R1 there. This one is actually just the same, but remember that normal force and friction force is actually, we handle it together because those two are just one unknowns. Any question about this pulling the wedge out? Darian,
Yes, sir.
do you have any question, Darian? Still okay?
Not really, because it's still the same, right, sir? With pushing it.
Yes. It's still the same. As long as you know the correct direction of the friction force, is supposed to be okay. So that's the logic behind it. So actually, when you draw the free body diagram in the exam later, I want to give a suggestion for you. I suggest you, okay? I suggest you to use this. This kind of ways to draw the free body diagram, okay? Because by doing that, you know exactly the component of the forces, and it will be much safer for it will be much safer for you guys to solve it using this way, by separating the normal force and friction force.
What you mean is separating the free body diagram to two parts, yeah, sir.
No, not two parts, but
No,
separating
but
the no. What I mean is, by just now I explained several ways to draw the free body diagram in the wedge, right? You can join the normal force and friction force as R,
yes.
or you can separate the normal force and friction force. Okay, what I mean is, I suggest you to separate the normal force and friction force.
Oh, I see. Okay.
Because by doing so, you can see clearly what is the component there. But for sure, you have to remember that friction force and normal force is just one unknowns, because the friction force there is normally the normal force multiplied by the mu, depends on the condition, right? If it's from the beginning, it's said that it's in the motion condition, then the friction force will be the same as mu. The friction force will be the same as normal force multiplied by mu k. But if there is nothing mentioned there, then the friction force will be equal to the normal force multiplied by mu s. Okay.
Okay, sir.
I think it's quite clear, right? For the pushing in and pulling out, right? Then I think I will delete this first. Okay. One more thing that I have to explain to you guys is the self-locking mechanism. Okay, self-locking mechanism. I need to explain to you guys about self-locking mechanism. Okay, for the self-locking. I think let's just draw it in the new slides. Okay. Now I want to tell you guys about the self-locking mechanism, right? When we discuss about it, right? I think it should be the copy from this. Okay, when we talk about pulling the wedge out, right? Okay, you have to know as well when you push the wedge in and pull the wedge out. You have to know as well that a wedge depend on its alpha, right? Depend on its alpha, the angle there. Okay, depends on its alpha. It can determine the alpha that can determine whether the wedge will be able to self-lock or not. So the condition of self-lock is the condition where after you push the wedge in, okay, after you push the wedge in, okay, then after that you erase this particular force. So you delete that force P, okay. A soft locking wedge means that after it's pushing in like this, after it's pushed in like this, then when the force P is gone, the wedge will not be able to move by itself. So the wedge will stay there. Okay, if the wedge is staying there, then in that case, we can say that the wedge is self-locked. But sometimes there is one condition where the wedge, okay, sometimes there is one condition where the wedge will not be self-locked. Okay, so if the alpha is too big, okay, if the alpha is too big, after you push the wedge in, right, and the pushing force P is gone, okay, instead of self-lock there, what will be happening is the wedge will move by itself. The wedge will be moving by itself, so it will slide by itself, sliding out by itself. This kind of condition is the condition of wedge without self-locking mechanism. So that condition is one of the condition that you must know. The condition that you must know. So the condition of self-locking. Okay, the condition of self-locking. As you can see there, okay, the self-locking limit, right? The self-locking limit is alpha is smaller than the 2v. Okay, if alpha is smaller than 2v, okay, if alpha is smaller than 2v, then the wedge will self-lock. Okay, why it is like that? Anyone here can explain about it? Anyone here can explain about it? No one? Hello? Can you hear my voice?
Yes, sir.
Matthew, as usual, can you explain about it, Matthew?
No, sir.
Why the self-locking limit, okay, why the self-locking limit is alpha is less than 2v. So 2v is the self-locking limit. If alpha is bigger than 2v, okay, it will not be able to self-lock. Okay, now I ask you guys, when there is no force, okay, let's try to discuss using this, okay. When there is no force P here, when there is no force P there, okay, if we take a look at the free body diagram of the mass and the wedge, okay, the possibility of the movement is wedge going to the right or wedge going to the left? I'm asking you. The mass is going down or the mass is going up when there is no pushing force P or pulling force P?
To the right, sir.
So the wedge is going into the right, right? And the mass is going down, right? So basically, because of the natural phenomenon, right? When we have a mass, the tendency there, it tends, the mass tends to move down, right, instead of moving up, because of the potential energy there. Okay, whatever happening, the mass is always giving a force down instead of giving a force up. So it tends to move down. Okay, because the mass is tends to move down, then when there is no pushing force there, okay, the wedge tends to move to the right in this case, right? The wedge tends to move to the right. So the free body diagram of the in order to explain about the self-locking mechanism is actually quite close to the pulling the wedge out. So it's like this. So the mass is tends to moving down, and the wedge is tends to going to the right. Wedge tends to going to the right. So this is the free body diagram. So if we have alpha there, so this is, for example, my alpha. Okay, then I have here the phi1, phi. Okay, where phi here depends on the phi is actually tangent phi is actually equal to mu. Okay, remember, right? Tangent phi is actually the same as mu. Okay, then this one is phi. Yeah. Sorry. Okay. So basically, then we will have another phi here. This one is phi as well. This one is R1. This one is R2. Why I use this particular ways of representing the friction force and normal force is because it will be easier to explain it using this way. Okay. In this kind of condition, it will self-lock. Okay. In this kind of condition, it will self-lock. Why? Because as you can see, the tension, the wedge tends to move to the right. Okay, the wedge tend to move to the right, and remember that here the resultant of R1 and R2 is actually, it has more force to the left. Right? You can see it. By the angle, right? R1 has a component of going to the left, and R2 has component going to the left as well. So it will still resist the movement to the right. So this one will not move at all for this one. This one has self-locking mechanism. But if there is a time where the alpha is too big, for example, it's like this. Okay, the alpha is too big, and the value of alpha reach this one, the same as 2v. Okay, this is what will be happening later. This one is R1. This one is V, right? Then what you have here is sorry for that. This is the normal one, and then this is another. Okay, and this is R2. This is V as well. Okay, you can see there, right? This is the normal of the not the normal. This is the normal direction of the surface. This is the normal direction of the first surface. Okay, you can see that this one is V. Yeah. This one is V, and this one is V as well. And in this case, okay, what we have here, alpha is equal to 2v. And this is what will be happening there if alpha is equal to 2p. Okay, you can see there that the force R2 and the force R1, okay, is actually in the same line of action. Okay, the force R2 and the force R1 is actually in the same line of action. So in this case, the condition is like it's almost, the self-locking is almost gone. Then, can you imagine if we make sure that the alpha there is bigger than 2v? If alpha there is bigger than 2v, right? Then you can see that the R2 here, it will be more slanted to the left again. In that case, the resultant of the force R1 and R2 will push, okay, will push the wedge out. Because in this condition where alpha is the same as 2v, in this case where alpha is the same as 2v, right? The line of action of R1 and R2 is the same. It's in the same line of action. Okay, it's in the same line of action. So it will not still, it's still in the limit. Okay, in this case, is alpha is less than 2v. The total force of R1 and R2 okay, the total forces of R1 and R2, the resultant is still going to the left, which resists the movement to the right. So this one is still left self-locking. This one is in the limit. Okay, let's draw one more free body diagram which shows that in this condition, non-self-locking. Okay. I will try to make an extreme case like this. Okay, in this case, the normal force is like this. Sorry, the normal. This is the normal one, and this is the normal one. Okay, if we draw for R1, this is R1. Okay, if we draw for R2, this is R2. As you can see, in this case, right, in this case, alpha is actually bigger than 2V. What you can see there is the resultant of R1 and R2, okay, is actually will be pushing the wedge to the right. Okay, the resultant of R1 and R2 actually will be pushing the wedge to the right. Okay, so you can see here that previously it was in the same line of action, but this one, it will not be in the same line of action. So the total force of R1 and R2, it will be pushing the wedge to the right. So this is the condition of non-self-locking. And this is the condition of the self-locking limit. And the first one is the condition of not non-self-locking. This one is the condition of self-locking. So we have three conditions here. This is the first one, self-locking. The second one, self-locking limit, and the third one, non-self-locking. Okay, so basically, if the wedge have an alpha, the angle of the wedge is too big, what will be happening is there will be no self-locking condition. So after the pushing force is gone, okay, the wedge will move by itself. Okay, the wedge will pull itself, pull itself out like that. So this one is the condition of non-self-locking. Okay, the self-locking condition is, on the other hand, is the normal wedge that we normally use. Okay, after we push the wedge in, then it will stay there because it will self-lock. Okay, anyone have any question about the self-locking mechanism?
Sir, actually, I've been wondering about the why you use phi angle instead of alpha in the and
Which one? In one? Which one?
no, I mean why you use phi over alpha. I thought that
Alpha is the angle of the wedge. Phi is actually tangent. Tangent phi is actually mu.
Also, the angle of the N is not determined. It's not what I mean is R2 should be perpendicular to the wedge, right?
R should be
No, in the before.
No, R is not supposed to be perpendicular to the wedge.
Oh no.
Normal force, yes, supposed to be perpendicular to the wedge. R is actually a combination, combination between normal force and friction force. That's why we have tangent phi there. Tangent phi is equal to mu, right? That's why there is a mu here.
So it's not 90 degree to the wedge.
Of course not. The 90 degree to the wedge is normal force. R is combination of normal force and friction force. How can it be 90 degrees? Do you get it?
Oh, I see.
Okay, normal force is always 90 degrees to the wedge, to the surface, right? Normal force is always 90 degrees to the surface, but R has two components, normal force and friction force. The friction force for sure make it not 90 degrees to the surface, right? It will have an angle phi there to the surface. The phi there will come from this. Tangent phi is actually equal to mu, depend on the friction coefficient that you use. If you use mu s, so it means that it's from stationary, then tangent phi is equal to mu s. If it's from a moving condition, then tangent phi is equal to mu k, like that. You get it?
Because in the CL before, the wedge is 10 degrees, right? And I use 10 degrees for the normal force and the friction, and then just sigma Fy it with sin 10.
The wedge is 10 degrees. The wedge is 10 degrees means the alpha is 10 degrees, right?
Yes.
Yeah, so alpha is 10 degrees. There is no relation between alpha and phi. Phi depends on the mu. Okay, excuse me. Okay, I think somebody is keep calling me. Wait a minute.
Okay, sir.
Yeah, okay. Do you get it, Asar?
So
alpha
this is not for calculating F, yes, sir. The P, yes, sir. This is not for
no,
calculating.
this one is self-locking condition.
Oh.
It's different. It's self-locking condition. Self-locking means whether the wedge, after you push in, it will stay there or not.
Oh.
Okay. When you push the wedge in, then you remove the force P, right? There is several conditions that will be happening there. Okay. The first condition is the wedge will stay there. It means there is self-locking condition. Number one. The second one is at the self-locking limit. Number two, or the last one is self-locking, non-self-locking. Number three.
Oh, I see.
If alpha is too big, then it will not be self-locking. So it's relation between alpha and phi. Yes.
Sir, if the wedge is in the self-locking limit, is it still removable or is it still stuck in there?
It's still stuck in there. It's still stuck there. It will still stay there. So in order for you to ensure that the wedge is not non-self-locking, then use this. Because if it's in the still number two, equilibrium is still happening there. It's still equilibrium. Okay, it's still in the equilibrium condition. You get it? So self-locking, in the self-locking limit, it will still not moving at all. But if you are in the condition of non-self-locking, then it will move by itself. So the condition of when it is supposed to be moving by itself is like this. Okay.
So sir, both self-locking and the self-locking limit, both the object on top of the wedge will not move, still equilibrium like that. You mean?
Yes. But for the non-self-locking, the wedge will move to the right in this condition, will move to the right, and the mass will going down.
Slide to left down.
Okay, yeah. The mass will be going down, and because the mass is going down, then the wedge will be going to the right.
Okay.
Okay. Any other question about this?
Sir.
About the self-locking, yes.
For the not self-locking is like in the example of in the beginning that make the pipes wheel rolling, sir.
In that case, yes. In that case, yes. Yeah, the pipes will actually it's not roll. Yes, yeah, the pipe will roll in some way. Yes, it will roll. So why you have to know about this? Because this is what we normally use in order to design the wedge. Okay, that's the value that we normally use in order to design the wedge. Okay, so you have to ensure that the wedge is actually have alpha less than 2V. Although, as I told you, alpha equal to 2V, it's still in the equilibrium condition because the force is still in the same line of action like this, right? But it is better for you to avoid that. So the best way to design the self-locking is alpha is less than 2V. So this is what you have to ensure in order to make sure that your wedge have self-locking mechanism. And remember, alpha is actually the angle of the wedge. Phi is actually it has only a one relation to the mu. Okay, because tangent phi is equal to the mu, whatever mu they use. Okay, depend on the condition. If it's a stationary, then mu s. If it's a moving, then it's using mu k. Any other question here?
Can you go back to the slide at when you draw when alpha is less than 2 pi and etc.
This one you mean?
Yeah. Will the wedge not move to the left when 2 phi is more than alpha?
You mean this one, right?
Yeah.
Condition one, whether the wedge will move to the left if 2 phi is more than alpha? No, it will not. Because remember, R1 and R2 there actually is representation of the normal force and the maximum friction force, right?
Oh, so that
because
yeah. Okay, understand, sir.
Remember, right? Because
yes, sir,
R1 is actually the summation of the normal force and the maximum friction force one. Maximum friction force is actually based on the mu s. Okay, so basically the real condition, the real free body diagram will not be the same as this one. It will stay in the equilibrium, but the friction force will not be the maximum friction force. It will depend on the condition. It will depend on the, it will react to the, what is happening there. Do you get it, Matthew?
Yes, sir. So we'll never have to assume the wedge will go to the left, right?
No, the wedge will not be going to the left. Although it seems like the resultant is going to the left, but remember that one is based on the maximum friction force. And friction force, actually, we have to, friction force is actually depends on the condition, right? That's the thing. So in this case, the friction force will not be in the maximum state. it will still maintain the equilibrium. Do you get it, Matthew?
All right, sir. Thank you, sir.
Any other question here? Okay, don't forget to mark your attendance. Okay, I open the attendance until noon today. Okay, so actually, that's the thing that you're supposed to understand about self-locking limit, and non-self-locking. Okay, so for today, I will only concentrate on the basic theory of the wedge. So if we have a wedge like that, like this, okay, how can we draw the free body diagram? Okay, there are two ways. The first way is to separate the friction force and the normal force. But remember, because when we talk about wedge, we always talk about the extreme condition. So the friction force there is always depend on the mu s or mu k, depend on the condition. If it's moving, then mu k. If it's stationary, then mu s. Okay, that's why the N1 and the normal force and friction force is actually just one unknowns. So it's better for you to not separate the number of unknowns there, because F1, right, the friction force is actually equal to the normal force multiplied by the mu there. Okay, so, and because of that as well, we can represent both normal force and friction force as one summation force, as one resultant force, R. Okay, one resultant force, R with certain angle. Okay, the angle, okay, phi there, actually representing the tangent phi is actually the same as the mu that you use. If you use mu s, then tangent phi will be equal to mu s. If you use mu k, then tangent phi will be equal to mu k, like that. Okay, then if you want to represent it using this resultant force and phi, then we can draw the free body diagram like this. But you have to remember as well, when you design a wedge, okay, the value of alpha, the wedge angle, actually, we have to ensure that the wedge angle is small enough to ensure the self-locking. Unless you want to design wedge without self-locking. Okay, how to ensure that? Okay, we have to ensure that the self-locking is less, the alpha is less than 2 phi. Okay, and just now I remember to explain to you as well about the difference between the free body diagram of the wedge when we push the wedge in and when we pull the wedge out. And beside that, about the self-locking, okay, about the self-locking, right? I already explained to you as well that there are three conditions which represent the wedge. Depends on the value of alpha. If the value of alpha is small enough, less than 2 phi, it will be in the self-locking mechanism. But remember, this one, although the resultant of the R1 and R2 is actually going to the left, but in reality, it will not be going to the left because R1 is actually representing the normal force 1 and friction force, maximum friction force 1. Okay, maximum friction force is actually depends on the mu, but the friction force which is happening in the self-locking mechanism, yeah, most likely is not the same as the maximum friction force. So in reality, the equilibrium will still be there. The second condition is at the self-locking limit. Okay, self-locking limit is the condition where R1 and R2 in the same line of action, like that. Okay, but it's better for you to avoid it as well. It is better for us to use this if you want to design a self-locking wedge. Okay, then the last one is non-self-locking. Non-self-locking will be happening if the alpha is bigger than 2 phi. what will be happening if the wedge is non-self-locking and the alpha is too big, bigger than 2v, then after the pushing force is gone, the P is gone, the pushing force P is gone, the wedge will slide by itself. The mass will be sliding down, the wedge will be sliding out by itself. That's the thing. Okay. Actually, that's all the theory about wedge. Tomorrow, I think I will explain, I will give you several problem example. For example, this one, the answer is already there. Okay, this one as well. There are several problem example that I will discuss tomorrow. Okay, I think that's all for today. That's all the theory that I supposed to give you guys about the wedge. Any question about it? Nuki, do you have any question, Nuki? Nuki is gone.
Sir, so by the
Asar,
means
yes.
of the least force, we just use equilibrium, right, to solve P.
Oh yes, yes, yes. We just need to use equilibrium.
So,
And remember, wedge, yeah. When we discuss about wedge, right? It's always a point force. So there will be no sigma moment there. Okay.
Oh yes.
There will be no sigma moment there. Yes, Asar. Just now you want to ask another question?
So, where do we use the locking mechanism before the locking? I forgot the name.
The locking mechanism. Whenever we, it depends on the question. If the question is about locking mechanism, then you use locking mechanism.
Oh, I see.
Okay. So I just explained to you guys. If you want to design a wedge with locking mechanism, what you're supposed to do? What you're supposed to do is just to ensure that alpha is less than 2v. That's all. If you want to design non-self-locking mechanism, then make the alpha bigger than 2v. That's all. Okay, and if you want to, this free body diagram is just to explain about it. Okay.
Okay, sir.
Any other question? I think it's supposed to be clear enough, right? And tomorrow, don't forget, we have a class at 7 in the morning. Okay, and we will continue the discussion on the wedge, especially on the problem example of the wedge. Okay. I think that's all. That's all for today. Thank you very much for listening. Okay. See you guys tomorrow morning.
Thank you, sir.
Thank you very much, sir.
Thank you very much, sir.
Thank you, sir.
Terima kasih banyak, Pak.
Thank you very much, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.